Hi, so for today we're going to talk about the exact differential equation. And before I talk about exact differential equation, I would just like to thank all of you for supporting my YouTube channel. So I already have 2,000 something, 2,300 subscribers. So thank you so much for making this possible. So without you guys watching my tutorial videos, I wouldn't be here right now. So thank you so much for all of you for your support, and I do hope that on the next coming videos you will still be watching my videos. So thank you so much for that, and let's get started. So we're going to talk about exact differential equation today. And what is an exact differential equation? So exact differential equation, a DE is said to be exact if and only if we have this condition. Okay, if we attain this condition. So the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. And m and n, we actually know that m is the term composed of function of x and y that is associated with dx in our differential equation, and the n term is also a function of x and y that is associated with the dy in our given differential equation. And this is also called the test for exactness. Okay, if we're going to test for the exactness of a DE, we're going to use this formula. If they are equal, if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x, then it means that the DE is said to be exact. Well, of course, if it is not equal, then it is not an exact DE, but a non-exact DE. Okay? So, but in this case, we're going to talk about or solve problems uh, that are exact differential equation. And if we fulfill this, if we computed this to be equal in our DE, then to solve for the exact DE, we must be using these formulas. Okay, wherein the partial of derivative of f with respect to x, okay, is equal to the function of x, and y. And the partial of f, derivative of f with respect to y, is equal to the function of n x1. Okay? So where f is the solution to an exact DE. So in other words, if we are solving exact DE, we need to first test for its exactness. And after we test it for its exactness, to be proven that this is an exact DE, we're going to use this formula to solve the exact DE. Okay? So let's try to solve this. Okay, so in this exactly, you will be recalling your knowledge all about partial differentiation, of course, integrals, okay, and some of algebra. So let's try this. Solve the following exactly. So as we all know, again, in our previous video, we discussed that all the terms containing x, y, okay, with the dx, that is our m, and all the terms here with our dy is equal to n. So this should be equal to 0. Okay, I forgot to write it. So to solve this class, okay, we're going to test for its exactness. That is the partial derivative of y, of m with respect to y is equal to the partial derivative of n with respect to x. So we must test this in order for this DE to be exact. So first of all, we're going to get the partial derivative of m with respect to y. So we're going to get the derivative of this with respect to y. What is our m? This is our m, 3x squared y minus 6x. Okay, so take note that this is a partial derivative. So if we get the partial derivative of m with respect to y, we're going to treat other constants aside from y, okay, or other variables aside from y as constant. So again, we are differentiating with respect to y. So all of the other variables other than y is constant. So in this case, we can say that if we get the partial derivative of this m with respect to y, okay, we will be treating x as constants because we are differentiating with respect to y. So what will happen here is that 3x squared will be constant, okay? So that is a constant, and differentiate now y. The differential of y, or the derivative of y in this case, is 1. So this should be multiplied by 1. Okay? Minus, again, if we differentiate this 6x, 6 is a constant multiplied by x, which is also a constant because we're differentiating it with respect to y. So this 6x is actually will become 0 because 6x is actually a constant. So what will happen? The partial derivative of m with respect to y would now be 3x squared. Okay? I hope you get it. So the other one, we will try to get the partial derivative of n with respect to x. Okay? And that is equal to n as a function of x and y. And here is our n. So our n is x cubed plus 2y. So what will happen is that if we get the partial derivative of that, we will be having what? This. The partial with respect to x of x cubed plus 2y. Okay? So what will happen? We are differentiating with respect to x. So any other variables other than x is considered as constant. So in this case, if we differentiate it with respect to x, this should be 3x squared. Plus, we have a 2y here. And any other variable again, except for x, is considered as constant. So, the derivative of this, 2 times y, where y is also a constant because we're differentiating with respect to x, that is equivalent to 0 because the derivative of a constant is 0. So what will happen? We have 3x squared also. Hence, we have proven that this given DE is an exact differential equation. So hence, therefore, we can conclude that this is exact. Okay? And now, in order for us to solve the exact DE, because this is not the final answer. This is only a test for exactness of the DE. But this is not the final answer. In order for us to get the final answer, we shall be using our formula a while ago, which is this. The partial derivative of m with respect to x is equals to the function m as a function of x and y, and this formula also. So first, we're going to solve the partial derivative of f with respect to x is equal to the m as a function of x and y. So what will happen here? We have the partial of f with respect to x. Our m, again, our n is 3x squared y minus 6x. So we have 3x squared y minus 6x. If I'm going to cross multiply dx, or partial of x, with on the other side of our equation, we have partial of f, okay, we have 3x squared y minus 6x partial of x. Okay? And we say, class, that f is the solution to our differential equation. This is partial of f. So if I'm going to integrate both sides of our equation, I shall be getting f here, which is this f is the solution to our differential equation. So what will happen? This should be equal to. Now, how do we integrate this? This is with respect to dx. Okay? So, partial of x. So, we can actually, what? By properties of integral, we can distribute the integral sign on this because this is a difference, and also the presence of dx. So, we have 3x squared y dx, or partial of x is still okay, minus the integral of 6x partial of x, or simply dx. Okay? So what are we going to do? Okay? We are differentiating or integrating. I'm sorry. We are integrating in terms of x. So any other variable rather than x, okay, should be treated as constant. So this y is treated as constant. and we have no constants here but the 6, okay, and also the 3 here. So what can happen here is that it should now be equal to, I can factor out the constant 3 and y inside outside of the integral. So we have 3y integral of x squared dx minus 6. I can factor out 6 because that is a constant, x dx. So integrate. So we have 3y x cubed over 3, that's the integral of x squared, minus 6 times x squared over 2. Okay? Plus, of course, when we do integral, we have a constant. But here, the constant is actually what? Is in terms of q of y. I will explain later after we simplify this. Y q of y. Okay? So, we can see that 3's will cancel. 6 over 2 is simply 3. So, we have now x cubed of y, x cubed y, minus 3x squared plus a constant q in terms of y. Why q of y? Why not simply c? No, note also that this is plus c. This can be also plus c. But more specifically, this is q of y as a function of y. Why? Because we know that this is now the f. Okay? This is now the f. The whole function is the f. And our original given is this, partial of f with respect to x. So, if I'm going to differentiate this with respect to x, I shall be arriving at this. Okay? Because that is the opposite of integration, the differential derivative. Okay? So, even if I'm going to add, let's say, q of y, even if I'm going to add y here, let's say q of y is equals to y, and I'm going to get the partial derivative of this f with respect to x, okay, I shall be still arriving at this answer. Why? Because if I'm going to get the partial derivative of this f with respect to x, even if I have a y term here, okay, the result would always be this. Because y here is treated as constant. And I hope you get it. So, okay, so we have this q of y here. Okay? So, because if we differentiate it with respect to partial of x, this would be still 0. Okay? So, this is a constant but in terms of y because we are partially differentiating it with respect to x. And I hope that's clear. So, because this q of y is important, so let me just erase this. I hope you got it. Okay? So, again, is this now the answer? Yes, we can use this as our answer, but we don't know the value of q of y. So, what are we going to do is, so, we are not yet done in our solution. Let's take note that we only get the partial of f with respect to x. But how about the partial of x, partial derivative of f with respect to y is equal to the n as a function of xy? Because that is our formula. That is our second formula. And if you get this, partial of f with respect to y is equal, what is n in terms of xy? That is x cubed plus 2y. X cubed plus 2y here. So we have x cubed plus 2y. And if we're going to cross multiply that partial of f with respect to y, okay, cross multiplication, okay? So we have now partial of f is equal now to x cubed plus 2y, okay, dy here. And we are after the f, so we're going to integrate both sides to get the solution of this d. So we have f is equals to the integral of x cubed dy plus the integral of 2y dy. Notice here that we are integrating in terms of y. So any other variables, okay, other than y is considered as constant. So in this case, I can factor out outside of the integral this x cubed dy, and I can factor out 2 the integral of y dy. So if we're going to get that, we shall be having x cubed of y plus 2y squared over 2. Okay, this should be cancelled. And plus, okay, if we have a q of y here, which is a term that is purely in terms of y. So we shall be having also another term here, a constant r of x. Okay? Because again, okay, I'm going to simplify this first. X cubed y plus y squared plus r of x. Because again, okay, if I'm going to differentiate this with respect to y, even if I have a term x here, pure terms in x, the result will always be this. Okay? Okay, so even if I have an x term here, okay, if I'm going to partially differentiate it with respect to y, this is treated as constant. Okay, so I will be still arriving at this answer. It's merely more of a constant, but it is in terms of x because we're doing a partial derivative. Okay, so sir, what is the final answer? So we need to determine the q of y and the r of x. So here we have f is equals to x cubed y plus y squared plus r of x. And here we have x cubed of y minus tx squared plus q of y. Notice that they are both equal to f. So if I'm going to equate, okay, equate the f, okay, the two f's, okay, so we have first we have this, let's say x cubed y plus y squared plus r of x is equal to the other f here, which is x cubed y minus 3x squared plus q of y. Okay, so we're going to find the values of f of x and q of y. As you can see, x cubed y would cancel. Okay? X cubed y would cancel. And by inspection, our value of r of x on the other side is negative 3x squared. Why? Because r of x is purely in terms of x. And we have a term here on the other side that is purely in terms of x, which is negative 3x squared. Hence, r of x is equal to negative 3x squared. How about q of y? Here is our q of y. And then on the other side of the equation, we have it purely in terms of y. So that is equivalent to y squared. Okay? So, upon determining r of x and q of y, we shall be getting the answer by simply substituting the value of q of y here in our first f function or the r of x here in our second f function. Only that this f, okay, this function f will be replaced by a constant c. Okay, because whenever we do integration, we are having a constant c, which is a very common or a general constant c. So, if I'm going to use this, I will be having x cubed y. The general solution for our d is x cubed y plus y squared plus, what is this? R of x, okay? That will become negative because this is negative 3x cubed. So, that would become negative 3x squared, okay, is equal, is equal to f, which is equal to c. And this should be now our general equation. Okay? Sir, can we use also this? Okay, if we use this, no problem. So if we use the other one, the other f here, no problem. We have x cubed y minus 3x squared. So x cubed y minus 3x squared plus the q of y, which is plus y squared. And the other side of the equation, the f will now become the c. So, in other words, even if you use the first f as a solution or the second f as a solution, you will still be arriving at the same answer. And hence, this should be our answer for the exact DE given in the problem. Okay, let's try to solve again another problem. For problem number 2, we have 2x cubed minus xy squared minus 2y plus 3 dx, okay, minus x squared y plus 2x dy is equals to 0. Notice again that this should be our m, Okay? And this should be our n. So upon performing test of exactness, partial of m with respect to y, that should be equal to partial of n with respect to x. So upon performing that, we shall perform that. Okay? Partial of m with respect to y. Okay? So this should be the partial of the function m with respect to y, which is 2x cubed minus xy squared minus 2y plus 3. Okay? So, as you can see here, this term does not have any y terms in it. So, any other variable except for y is considered as a constant. So, the derivative of this constant is 0. 2x cubed, the derivative of partial derivative of 2x cubed with respect to y is 0. How about this? Okay, with respect to y, that is 2y. Okay, but since x is considered as constant, that should be 2xy. Okay, so this should be considered as constant. You try to differentiate this, and this term, okay, with respect to y is minus 2, and this term with respect to y, that is a constant, plus 0. So hence our partial derivative of m with respect to y is negative 2xy minus 2. Okay? And we shall get the partial of n with respect to x. Okay? That is, of course, this is a negative sign. So if I'm going to distribute the negative sign, you must do that. Negative x squared y minus 2x. Okay? So if I'm going to differentiate that with respect to x, okay, this function of n, so any other variables aside from x is considered as constant. So get the derivative of this negative x squared y with respect, partial derivative with respect to x. So that is negative 2xy. Okay? And partial derivative of this with respect to x, that is minus 2. Hence, negative 2xy minus 2, negative 2xy minus 2. Therefore, we have an exact DE. And again, we shall be solving the exact solution or the solution for this DE by performing again the partial of m, okay, with respect to x, and that is equal, okay, not partial of m, but partial of the function f, and now equal to the m as function of xy. Okay? So, again, if I'm going to cross multiply this should be partial of f, okay, multiplied by m. What is our m? 2x cubed minus xy squared. So we have 2x cubed minus xy squared minus 2y plus 3. Okay? So cross multiplying this, we have now dx here. So if I'm going to integrate both sides so as to get the f, okay, because that is our solution again. So I have here f is equal now to distributing the integral in the dx sign. We have 2x cubed dx minus xy squared dx minus the integral of 2y dx plus the integral of 3 dx. So, and again, we are integrating with respect to x. So, any other variable aside from x is considered as constant. So, we have, I can factor out 2 outside of the integral sign. I have x cubed dx here. I can factor out y squared here because we are integrating with respect to x. So, y squared, integral of x dx. I can factor out 2 and y here, 2y, because we're integrating with respect to dx, minus 2y integral of dx. I can factor out 3 here, 3 integral of dx. So, in integrate, so we have 2x raised to 4 over 4, okay, minus y squared, x squared over 2, minus 2y, the integral of dx is simply x, plus 3 times the integral of dx is simply x. And of course, plus q of y, okay? Don't forget the q of y. And again, we can simplify. 2 over 4 is 1 half. So, yeah. So, we don't have any other to simplify. So, let's rewrite that. So, we have 1 half x raised to 4 minus 1 half x squared y squared, okay, x squared y squared over 2 minus 2xy plus 3x plus q of y. And that is our first f. How about the second f? So partial of f with respect to y is equals to the n in terms of xy. So partial of f, n of xy is, don't forget the negative, negative x squared y minus 2x. And of course, this is multiplied by dy because I cross multiplied dy here. So if I'm going to get, again, the integral of both sides of our equation, we shall be getting f is equals to integral of negative x squared y dy minus integral of 2x dy. So, any other variables aside from y is considered as constant because we're integrating again with respect to y. So, we have negative x squared integral of y dy minus, I can factor out 2x here because we're integrating with respect to y or dy. So, what will happen? We have negative x squared y squared over 2, okay, minus 2x integral of dy is y, okay, plus r of x, okay, don't forget that, a constant in purely in terms of x. So we have now f as negative 1 half x squared y squared minus 2xy plus r of x. And the last step is actually to determine the value of r of x and the q of x. So, if we are to equate the two, okay, we should equate first this. We have 1 half x raised to 4 minus 1 half x squared y squared minus 2xy plus 3x plus q of y is now equal to negative 1 half x squared y squared minus 2xy plus r of x. Okay? So as you can see, upon simplifying, we can cancel out some terms. So we have negative 1 half x squared y squared. We have negative 1 half x squared y squared here. Okay? So we can also cancel out negative 2xy and negative 2xy here. So we shall be determining what is the value, or we shall determine what's the value of q of y. Okay? So q of y as a function of y on the other side of the equation, there is none. Okay? So that is 0. Because there is no other term here that is purely in terms of y on the other side of the equation. That definitely that is equal to 0. And r of x is now equal to the x term purely expressed in terms of x on the other side of the equation. So we have r of x. On the other side of the equation, we have 1 half purely in terms of x, 1 half x raised to 4, plus here, we have 3x. And hence, we can use this one or this one to obtain our general solution for this exact DE. Okay, if we choose this one, then definitely the answer is this one already because q of y is 0 and you're going to replace f with simply c. So, our answer is now c is equals to 1 half x raised to 4, okay, minus 1 half x squared y squared, okay, minus 2xy plus 3x plus 0 because the value of q of y is 0. So hence, this should be our general solution for the exact DE if we're going to use this. How about if we're going to use this? It's still the same. Okay? If we're going to use this one, you will be arriving exactly at the same answer. Because r of x is equal to 1 half x raised to 4, which is this, and plus 3x, which is this. So, you'll be having the same answer. Or you can simply multiply this by 2 and get the answer if you want to eliminate the denominator. But for me, it's okay. It depends on the multiple choice or the choices maybe. But this is still acceptable, or so we can also multiply this by 2x raised to 4 minus x squared y squared minus 4xy, okay, plus 6x. Okay. That is still the same. That is a general solution for our for our second example of an exact differential equation. So I hope you guys enjoyed the video. So thank you so much for listening. I'll be having a part 2 on this, maybe involving trigonometric functions, so that we can solve also a DE involving trigonometric functions. So thank you so much. I hope you learned something from this video, and don't forget to share it with your engineering friends, especially those who are taking differential equations. So thank you so much, and God bless.